Hey everybody, hope you're doing well, and welcome to the third installment of the Neural audio plugin live stream. So this is a competition and initiative that we've teamed up. We being the audio programmer Cosmo, represented by Andrew Fife here with us, and also Christian Steinmetz, to raise awareness about AI and audio plugins, and to get some education, some more education and more awareness around this space. And so for the past couple of weeks, we've been doing some live streams with some really influential people in the space who have been talking about ways that you can build audio plugins using neural networks and AI. And if you haven't seen those, or if you've missed those, then you can go back into the channel, and you can find out. You can watch those back. And this week we're continuing that trend with two great guests. We have Philippe Esling from IRCAM, and we have Jatin Chowdhury from Chowdhury joining us again, frequent guest on our channel. Before we started, just wanted to go through a little bit of the basics just around the competition and around the initiative itself. So there's been a lot of really positive buzz about the competition. We've been seeing quite a few people in our audio programmer Discord channel that have been talking about collaborating, which I think is really exciting. So we've said this the past couple weeks, and I'll say it again, that if you're a person that isn't very familiar with this space, but you want to get involved, please join the audio programmer Discord if you haven't already, and just let everybody know that you're interested in getting involved, and maybe you have some skills with Max MSP and Rainbow, or with MATLAB, or with Juice, and you can offer skills in that area and are looking to team up with other people who may be more familiar with the space and don't have the skills that you have. So we allow teams up to 4 to participate, and we hope that you can get involved. If you're looking for information about the competition itself, you can find information on our website, theaudioprogrammer.com/neural-audio. And there it has details with all of the prizes that we have for the winners, also our sponsors, and I will pull those up really quick because I don't want to start without giving a mention to all the people that are supporting. So I will take a moment to share my screen real quick here, go off script, and there we are. So this is the webpage that has all the information about the competition. So big shout out to our sponsors: TikTok, Cosmo, Juice, Cycling 74, GPU Audio, and MathWorks for their participation and helping to supply prizes for the winners. And all of the information that you need about the competition is right here. So this is also the portal for you to be able to enter the competition itself as well. And a list of the prizes are there. I've gone through those before, and I'll leave those to you to go through as you'd like. Here's also a list of popular SDKs that you can use to create your audio plugin. So I hope that this answers your questions. But if you have other questions, please feel free to just ask in the live chat, and we'd be happy to help. And yeah, with that, I think that we can go ahead and get started. So I will pass the microphone to Andrew, and he will do our first introduction for the talk.
Cheers, Josh. Yeah, super excited to introduce our first speaker for this session. So we've got Philippe Esling, who's here from IRCAM. Philippe leads the ACIS group at IRCAM, does a lot of great research in neuro audio, worked on the RAVE neuro audio models, if some of you are familiar with RAVE, along with Antoine Quillion. And yeah, they're doing some great work there in furthering neuro audio, the research at IRCAM. So I'll pass it on to Philippe, and he's going to be giving his presentation on AI in 64 kilobytes. Take it away, Philippe.
Thank you so much, Andrew, and thank you everyone for joining. So I'm really excited to show you this quite weird presentation, actually, because it's an idea that popped in my mind. So it's really, I think, the time to discuss AI as a really fundamentally efficient oriented problem. So what I'm trying to say, so as Andrew brilliantly introduced, I created this group called ACIDS, which stands for Artificial Creative Intelligence and Data Science. It has a true meaning. And basically, we're doing like lots of different research. So a few years ago, I did this model called FlowSynth. So FlowSynth is a way to, you take a synthesizer, but you just drop a wave file on the like deep model, and the model is going to find the parameters of the synth that sound closest. So basically now you have a patch. So it's kind of waveform to parameters. So one example, another example that you might heard as well is rave. So rave is a case of what we call timbre transfer. So it's like real-time plugin where you can put like some audio in, and then it will change the audio to like a target domain. And you can do that for kind of any form of instruments. And so there is like voice and darbuka at the same time. We also extended this ideas to have like a real-time control based on like sensors. So here you have another rave model, which is basically controlled by like a gyroscope and motion sensors. So basically, we're just connecting the dimensions that you saw in the previous one to yet another model. So yeah, just because it sounds cool, I'm gonna leave like the drums. Okay, and we even went up and currently are working on this little thing called NeuroRack. So NeuroRack is actually the embedded version. So I don't know how well people are hearing this, but this is actually, so this is a modular version. So we actually soldered and built this whole thing. And behind right now, there is now a Raspberry Pi model. So I find it cool that always in these type of shows, people are just showcasing their work. So we have lots of interesting work, I think, and we're trying, the overarching goal is to push the limits of creativity through the use of machine learning. But I'm kind of here to say that, yeah, machine learning lately kind of suck. And I mean, modern deep learning is everywhere. So, we have like state-of-the-art results and it's super impressive and applies to all domain. But for me, there is like key problems that we need to address. And especially in the audio field, I think for me, it makes no sense that we are getting to networks that have billions of zillions of parameters. I mean, it's a Penzer approach. I mean, I started working in this field on the premises that I was working on something intelligent. And for me, like having this correlation between accuracy and size makes kind of no sense. So, and even worse, if we are looking at what we are trying to achieve is actually something creative. So something which is lightweight and constructive. But we have models that are extremely demanding in energy, time, and memory. And these questions are usually completely obviated by the fact that you need to get that new sound, okay? So maybe you're saying, well, okay, this guy is a buzzkill. So how much is the case? So what I'm saying is that if you look, and this is like several studies have shown that there is like several eras in the machine learning game. So before 2012, actually the evolution of the computation power used in machine learning was following Moore's law. So Moore's law is like you double every 2 years, approximately. And since approximately like the layer like really the expansion of deep learning, there has been like a second era where you see like doubling, but every 3 to 4 months. And if we zoom in on this part, you can see actually from like 2012 to 2018, there has been like a 100,000 times increase in the amount of computation needed to get like new results. So what are the consequences of this thing? Of course, like the first and foremost is like environmental issue. And for me, like the really important aspect I want to stress out is in terms of audio plugins, we are really limited in what we are allowed to use if we want this to go into synthesizers and even more Eurorack of this stuff. And it's even less possible to embed these systems. So if you take GPT-3, for instance, ChatGPT everyone's talking about, it takes 175 billion parameters. And if you have a single GPU at home, you just have to wait 355 years to train it. So everyone's going to say, yeah, but of course, it's, it's kind of the game. But I think thinking also that the carbon footprint for training these things like driving to the moon and back, it's kind of shivering. And we recently actually shifted to work really on this efficiency issue. And for me, it's like kind of the new real goal that we need to attain in this domain. Like, for instance, this is a study that we just published in ICASP. I mean, it's going to be in the next ICASP. So these are all neural vocoders, so systems that are able to generate speech. And if you take like an original sound.
The corporation had agreed to spend £20,000 on alteration.
So of course, the most efficient model in terms of size and speed is going to sound.
The corporation had agreed to spend £20,000 on alteration.
Not really good. If you take diffusion models like stable diffusions and all this stuff, and you apply it to speech, you get excellent results.
The corporation had agreed to spend £20,000 on alteration.
But you see, there is like a factor 1,000 is in the energy that you need to use to get this like slight amount of increase. And you can find some models that actually only produce like 2 or 3 times increase.
The corporation had agreed to spend £20,000 on alteration.
And you actually get something which is excellent. I mean, it's not at the same level of diffusion, but I guess there is some like trade-off that you can make in order to find these efficient yet qualitative model. And what I'm trying to stress is, okay, we now have billions of parameters, and we know we don't want to go back to the time where we had crappy accuracy, but like having these things where you need 500 GPUs for 10 days, for me, it's even more like, how to say, blatant. If you look, the amount of gain we get in accuracy compared to the amount of parameters that we need to get this. So it's not to shoot in the face of those authors. I mean, CREP is amazing, but for pitch detection, for instance, not even multi-pitch detection, there was this algorithm called PIN, which is autocorrelation based. So basically it has like maybe 2 parameters, and it gets you a 99% accuracy. And then with the CNN, with 22 million parameters and 3 gigaflops computation, you gain like 0.009 accuracy. So I'm wondering, is it really worth it? And what about the original question, which means we can't really use models that are too demanding on Arduino, on Raspberry Pis. So it's almost impossible for what we're trying to achieve, which is neural audio plugins, which are basically something which is supposed to work all the time. Because if you go to like a live show and your 200 GPUs just fall down, it's not going to sound very cool. And yeah, I'm thinking about like the requirements of these type of platforms. So I think we can still try to set the goal to have the same accuracy, but how do we find those smaller models that still work? So today's question is something that is, of course, completely crazy. So don't worry. I know AI in 64 kilobits does not make sense, but the overall question is, can we do the same with less? And trying to kind of back off from this trend, which is, oh, I have a model that works, like multiply the number of parameters by 100. Oh, it works better. Amazing. So my question is, yeah, what would be more amazing is to have the same result by having 100 times less parameters. So Of course, the objective of 64 kilobits is extreme, but I don't know if there are some nerds here that follows this weird conference, but it's inspired by something called the demo scene. And when I was a young nerd in the making, I was completely amazed by this idea. So the 64K competition in the demo scene. So demo scene is just, creating like funky videos with code. And there was a specific type of video where you have to create by any means necessary something which only weighs 64 kilobits as an executable binary, but it generates like a very cool complex video and audio. So you can check it online, type 64K demos, and you're going to find like amazing videos that if you output it as an MP4 makes like several gigabytes, but it's a 64 kilobytes program that actually mostly generates everything. And for me, this is obviously different than from AI, but I find the goal is amazing. And so we're going to first review a few hypotheses where I think we can make this work, and also discuss some of the ML properties that shows that actually this is not so crazy after all. So first, I want to make some weird philosophical observation. Let's review the complexity of our problem. So imagine you observe the path of an ant, and you see the ant moving, and it looks like, whoa, the ant is making a very complicated path in the world. But if you look at this, you would say, oh, she might be extremely smart and doing something super complicated. But if you look closer, there are rocks that the ant is just avoiding. So I think first, complexity can be a consequence of the environment and not the program. Now, second observation on this, imagine you're seeing this pattern forming, and you're going to say, whoa, this is also quite a complicated algorithm that generates this. But if you were able to see the actual problem, you would just see that it's just a cube going through a piece of paper. So for me, this points out to the fact that we usually look at problems in the wrong way. So we are just looking at a bad projection of a higher dimensional problem. So if we could manage to find back the original dimensionality, it would be way simpler. Next observation, let's try to reverse. This is a weird thinking experiment I do with my students before they know the answer. And I'm guessing some people might know the answer. But imagine the only way to solve a problem you have is to have a straight line. And I'm stating that these two groups of points can be separated by a single straight line. And the question is, of course, but how can you do that? And that's a very good way if you are in a bar and you want to, brag about your new machine learning skills and lose some friends in the Bing. So basically, the problem is that, once again, you're not in the right space. So just, draw that on a piece of paper and then put your fist under the piece of paper and you can draw like a single line. So we want these simple solutions, but we want mostly simple explanations. And that's also this idea of disentanglement that we will see later on. Now, the second observation, which is quite more on the philosophical side of what is intelligence and what's an intelligent behavior, is this well-known Occam's razor principle. So the actual principle is entities should not be multiplied without necessity, or equivalently, the simplest explanation is most likely the right one. So a more formal way of describing this is the minimum description length principle, which I love, which is that comprehension is actually compression. So you can actually formalize that and say, let's say you have lots of models that can explain a data set. So here H is just because it's hypothesis space, right? So the MDL principle states this seemingly complicated formula, which just says that actually the best solution is not only, it's not only the one that is the best in describing the data, but it's also the one that is the smallest in terms of the number of bits, both of the model itself, so the smallest model, but also the smallest description of the data as encoded by the model. And I think this relates very well to, if we take the generic definition of machine learning, you know, what we're trying to achieve is that nature produced some relations, and we are looking at this relation. So we have one set and another set, and something's happening in between. And we say, oh, it's too complicated for us to understand. So let's just put some machine learning in there. Okay. And for instance, here you could say we have points, and we know that some points are yellow and some points are purple or pink. And basically, we're trying to find a way to know, okay, next point is going to be what? So we do this approximation where we find a function, and depending on the function and its parameters, we need a way to evaluate the quality, and then we kind of tune the parameters to find the best approximation of the function. So we are trying to change the behavior of the function. So actually, everything boils down to what function do we use? And if we use a too simple function, then we underfit because, yeah, we need more complexity. If we use a too complex function, there is this thing called overfitting. And we would like to find this optimal capacity, which is like the perfect mixture. So this kind of relates to the minimum description length principle. So everything kind of boils down to the choice of this function. And the weird thing is that there is this notion of model capacity. And if you think about the family of function that we can use, let's say we have this problem, which is a simple regression problem. So we could use a simple number, but we know it makes no sense. So let's say we use first a line. So the line is a bad approximator because this is clearly a quadratic problem. And we could go up to like any number of degrees in our polynomial, right? And you would say, yeah, kind of, why does the polynomial 18 does not include naturally the polynomial of degree 2? And of course it does. But the problem is just it's trying too well to fit. So how come more data helps there? It's because it's naturally regularizing. The more data you have, and the more you can just use a very complicated function, because it's never going to be able to go through all the points. So that's why we're getting to this situation right now. And this problem lies in what's called the bias and the variance of our approximation, right? Because we have a space, let's say this slide is now the space of all our possible functions. So we are looking for this best possible function. And the problem is we don't know what is this function f star. So we need to consider something which might be close. The problem is we don't have access to f star. So there is already a bias. Even if we find the best function in our considered function family, we're still going to have like incompressible error from the difference between like the real function and what we selected as an approximator. And then training on different sets of data is going to get us to have variance between the best possible function and our data. So the thing is, there is different ways to choose this family between low variance and high bias, high variance and low bias, and some good trade-off, right? So the problem in the variance is the discrepancy between the fact that we want to estimate the expected risk. So this, again, looks like a very complicated formula, but it's super simple. Means we're just trying to compute the mean of all the errors, but knowing all the points in the universe. So this means like we are trying to regularize on something we don't really know. So what we can only do is just take points. Instead of every point in the universe, we just take like discrete points. And so that's why we are kind of losing the best function that we could have. And now in deep learning, there is something very interesting, and I think it's going to be the like key argument that I'm trying to get to. We used to think that overfitting was exactly these type of curves. So it means, yeah, there is a complexity of the function. If the function is too complex, it means that there is a point where it's going to overfit, like we saw with the simple two-dimensional plane. But actually, recent research have shown that there is this overparameterized mode. And this is exactly the modern like point where we are now, when you have like so many parameters that it starts to interpolate. So, and that's also a problem. So we don't really know how much this is memorization. So if we take this, you can actually reproduce these results at home. You can see that if you go over like a completely ludicrous amount of parameters, then it's entering this new interpolation mode, and it looks like there is no end. So this is also a new topic in deep learning called the scaling laws. You can look it up. So why overparameterization works? And I think there are several potential explanations, but one potential explanation that I like is that actually, imagine now the loss landscape. So it means what's the error we're going to get depending on the values of our parameters. So if we are in 2 dimensions, I mean, we have a single parameter and we're trying to find like the minimum of this function. So if we get stuck in this minima, it's very hard in the training to try to escape or find a route to go from one solution to the other. But if we add an extra parameter, even though we don't really necessarily need it, it becomes exponentially easier to find a way to go around this problem. And I think overparameterization simplifies the training and we find a better solution, but we don't really need the final solution to have all of these parameters. And so this is kind of confirmed by several ideas. And the first is mode connectivity. So mode connectivity means that an efficient solution might live in a subspace of your whole space of solution. So there is a huge potential to simplify the models we're using. And this means like if you do several models, then you have like all these valleys of several different models that perform the same, even though you change all the parameters. You can go from one, you interpolate one model to another, and you still get the same accuracy. Which means that if you have this valley, obviously you can project, and projection means reduction, and reduction means less parameters, but with the same accuracy. The other big thing, I think, and it's still being debated, but I'm pretty sure it's true, that the information bottleneck theory shows that there is 2 periods in training. So one that tries to maximize the material information, and the second one that naturally performs compression inside the network. So meaning that naturally, these type of models are going to tend to find sparse solutions and needing less parameters than we think they do. So I want to show quickly some form of model reductions. So there has been like this idea of reducing models is quite old. So it's been proposed in like 1990 by Yann LeCun. So it was called optimal brain damage. And usually it's been for a very long time very hard to train these models. So basically you have poor compression and usually use 3 major techniques, which is either compressing the network, so quantizing, distilling, or transferring, for instance, and growing the networks, which means the opposite way around, or pruning, which is trying to remove like the useless parts. And I want to stress out one thing we've been working on, which is called the lottery ticket hypothesis. Even though I'm not sure it's the best solution to this problem, I think it's super beautiful. So I guess it's worth looking at least. So model reduction, the first thing you do, let's say you have a big network, you can just try to quantize the weights. So it just means you've been training your network on 32, 64 bits, and you're just thinking, oh, okay, let's just replace the weights by classes. And so we can use, like, for instance, 2-bit reduction. So the idea is to keep the overall distribution, but to smartly find a way to just reduce the complexity. So basically here you're reducing the size of your network by 16, which is already something. So that's cool because you reduce the disk size. So if you work with Arduino, Raspberry Pi, it's quite cool, but usually you get like quite shitty results because, of course, 2 bits of information is a huge loss if you're talking about, audio. The second, even worse way would be to do like binary neural networks, but it seems that it works pretty well, and then you just have an output layer which is not binary anymore. But of course, it's the same issues. And some other model reduction that works quite well these days is called knowledge dissipation.
Uh-oh, looks like we may have a technical problem. Let's wait and see if he comes back. He needs to restart. So thanks to everybody who's been tuning in so far. And yeah, we'll just give Philip a little time to maybe start up his computer or to get back with us. In the meantime, just wanted to point you out to some details for the competition again. Once again, if you're looking to get involved with the competition and you're curious about how to get involved in the rules, be sure to check out the webpage, which is theaudioprogrammer.com/neural audio. And let me tell you a little bit about some of the prizes here. So I'm just going to pull this up really quickly. And 1 second. Yeah, so we have some great prizes that are coming up from... Oh, are you back with us, Philip? I see your head moving.
Yeah.
Oh, you're back?
Yeah,
Okay, great.
Yeah.
You
I'm
vanished for a
sorry.
moment.
Yeah, there was a problem with the.
Yeah. Okay, cool. Well, we'll discuss. I'll come back to that later. But go ahead, Philip. Yeah, now that you're
Oh,
back with
I'm
us.
sorry. When did I did
Oh,
start?
so he's frozen again. Sorry about this, everybody. We're just waiting to hear back. We'll wait for Philip to join us again here. So, oh, he's frozen. Okay, I'm gonna put some links in the chat for now. So we got theaudioprogrammer.com, neural audio. Philip, are you back with us?
Yeah.
Yeah, something seems to have happened with your Wi-Fi.
Well, something weird.
Yeah, it's a little bit strange. I'm not sure what's going on there.
Oh, sorry. Yes, absolutely. I think it might be the Wi-Fi.
I think you're back. I think you're good to go.
Yeah, I think. I mean, I moved to another location, hoping to get some better signal.
Yeah. Okay, great. Yeah, feel free to share away when you're ready to go.
Okay. So I don't really know where the presentation stopped.
So let's see. You were talking about. So I think you were in slide 22, I believe. 21 or 22.
Oh, wow. Okay.
Oh, no, I think it was on this slide, 24, at the beginning of 24, you cut off. Yeah.
There you go.
Okay, cool. So yeah, I'm almost finished with the weird model reduction argument. So just to finish, the idea is to try to use a way to compress your model by using a big model to teach the smaller model, and this allows you to obtain truly smaller networks. So there is lots of different approaches to compression, and I'm just gonna move on because I really wanted to show you this idea of pruning has been around for quite a while, which is we take these big networks and try to identify where we can just remove things. So you initialize your network, you train it, and then you try to find a way to select and remove parts of your network. The problem on this is even though you try to select and prune, it's usually mostly not very well working. You can remove maybe half of your network, sometimes a little bit more, but it's really disappointing. Recently, there's been this thing called the lottery ticket hypothesis, where inside these randomly initial
Uh-oh.
accuracy than the original networks. And in image,
once he comes fully back, I'll ask him to repeat.
they even show like a weird
Philip, can you hear us?
an amazing feat that these subnetworks, which are like 10 times smaller than the original, are performing better. And they show a vast improvement on the V.
We're just waiting for him to come back online, and we'll let him know.
Better accuracy than bigger.
Philip, can you hear us?
Yeah.
Are you there, Philip? If you are, it seems the Wi-Fi keeps breaking up on us.
Generation, and really try to add the state so that we could actually embed it network. And you can go up to, and you can use the models. It allows to do like high quality 40 kilohertz synthesis and 25 times.
Wow. Philip, can you hear us?
Yeah. Hello.
Oh, yeah. Okay.
Wow.
Yeah,
I'm so sorry. I don't know what's happening with the internet connection, apparently.
Yeah. Yes. Yeah. It's strange that it just started happening. Yeah. So I think we lost you for a couple minutes there.
Oh, again. Okay.
What slide were we? Would you mind starting from the slide that you were originally at, Philip, which was on 24, I believe?
Oh, wow.
Yeah.
Okay.
Yeah. You
Nice.
were around for quite a while.
Yeah, sorry about that. Yeah, so I spoke.
Right, you were on a roll though. We could hear you dipping in and out. You sounded like you were on a roll.
I was completely on a roll. So I guess everything I said, including the thing on network pruning, for instance.
I think we caught some of the network pruning, and then I think just after the network pruning, it started
Do we
to.
get that? Oh, just switch to like the end of the lottery ticket hypothesis. I'm just like sitting on the router, so my guess is I can't get a better signal here. So can you hear me?
Yep, we can hear you.
Okay, I'm gonna try to finish this. So basically, the idea of network pruning is to eliminate like unnecessary weights from like neural networks. And basically, you take your network, and once strained, you just select and prune part of the network. So the problem with these approaches is that you usually kind of lose most of the accuracy. So it's a very interesting approach, but at the same time, it means like you lose every accuracy. So you can probably remove like half of the network, but not really much more. So recently, we've been working on this thing called the lottery ticket hypothesis. And this states that inside these randomly initialized network, like you have very powerful small networks. And if you could train these subnetworks in isolation, you would get like a higher accuracy than the original model. It sounds crazy because it means that you have very small networks that perform better than very large networks. But actually, they showed this in image that you can get like 90% of the network removed and you get a better accuracy than the original network. And you can even go up to 95 and even 99.5%, and you don't lose any accuracy in the process. So I think this is quite amazing because it shows that there is some potential to find extremely sparse, extremely lightweight versions of like deep networks that are actually performing at least the same or even better than like huge model. I think these kinds of confirm this intuition that we don't really need these huge models. We might need them to find the solution because it's easier to like move across the loss landscape. But in the end, like there is a simple solution that exists inside these huge, crazy models. So yeah, I'm checking if, yeah, I'm still connected. I think I'm on the sweet spot of my internet connection. So yeah, thank you. So yeah, I'm just gonna move to show a few of the things we've done with that. And so basically, I showed quickly this rave model that we've been developing with Antoine Caillon. And so this was kind of the opposite way around. We started by doing like trying to find the most efficient way to do generation. So basically, the whole thing relies a lot on this multiband decomposition, and this multiband decomposition allows to have a very lightweight model. So this gets us the property that we have like high quality 48 kilohertz synthesis with 25 times real time on the laptop CPU. So you get this kind of results where, so this darbuka is like completely generated by the model, and we can generate like an infinite amount of this super crisp and super like high quality audio. So if you haven't had the opportunity, you can go play with the model. And the cool thing is like timbre transfer that I showed. We tried some weird stuff, but one that I really like is, so we take this violin sound, for instance, and we give it to model that we train on voice, and it's going to get you this. And so this cool thing is that we can do like polyphonic unconditional generation, like for every type of signals. And we did some like artistic collaboration with that. So we won the Ars Electronica. I mean, Alexander Schubert won, based on the work we did together, the Ars Electronica Golden Nika Prize. So we're quite proud of that. I'm going to switch a little bit faster because we lost a lot of time, and I'm sorry about that. So you can go on our GitHub. You have like both the original Python model, so you can train your own model. There is pure data max MSP version at NNTILD, and we even developed a small VST called Rave VST. So then you have like the videos I showed you earlier. And lately, and it's like kind of the latest advance in the like kind of rave model. So with Ninon Devey, we've been working on the idea of trying to have more control, because you know you can do transfer, so you put your voice and it gives you darbuka, but you don't really. It's not enough for us in terms of how creative controls we can get. So basically, we added a mechanism where we can explicitly try to put some features, like well-known features such as centroid, but we can also put weird stuff like boominess and such. So some examples of results. So you can find this paper in IRCAM. It's called NeuroRave. So basically, it's a mix between rave and this NeuroRack I showed you. So let's say we start by something which we generate with the model. So this is generated by rave, but we can't really control like specifics. And adding this new mechanism, we can actually say that we want to change, for instance, the bandwidth of the signal following a simple Eurorack signal like a sinusoid. We can control more exotic stuff like booming. Or sharpness. And the cool thing is that we can actually combine the timbre and the attribute transfer. So for instance, so yeah, sorry, it was not clear really. We used the darbuka from the previous model generation and we pass it to a second model, which is trained on Japanese voice. So it basically spills out this. And then we can also on top control the transfer of the attribute. Okay, and so yeah, I just wanted to say also the weird stuff I talked about on the lottery ticket hypothesis is also something we applied like these past years to like music information retrieval, where we can have like networks 10 times smaller that are 100 times more efficient, and you get actually even better errors on some cases. So it's really, I think, kind of a proof that we can really get lightweight models instead of huge crazy models. And we try to apply that like for constraint platforms. And so basically what we did is try to get down to the 80 mega 2000, which was a little bit crazy. So the problem is like doing this actually destroys the audio quality, but we managed to do some accurate model that still gets you like good synthesis and on a Raspberry Pi 1. So I think it's already quite a win, and hopefully, I guess in the upcoming years, we're going to try to reduce even more the models so that we can have them like simple models that perform well and on like energy efficient devices. So I guess I'm going to stop there because I outrun time. So yeah, just showing this last thing. This is the circuit that we mounted to do like a, we actually created our own board like this, and like all the design is also open source. So if you want to recreate it at home, you can. So thank you, and sorry for like the weird connection problems, but I would be happy to answer a question if my internet allows.
Great. Thank you so much, Philip. That was great, and thanks for the quick recovery. And yeah, this is what a fantastic talk. And what we'll do is we'll give a couple minutes or a couple seconds for some people to um, ask any questions that they may have. In the meantime, I was wondering if you could just talk a little bit about your background, how long you've been at IRCAM, and what exactly your responsibilities are there.
Yeah, actually, so I did a bachelor in mathematics and computer science, and then I mean, I also created like a weird electronic music production label where we did some vinyls, and I was lucky enough to stumble upon the masters at IRCAM, and I did my PhD thesis on machine learning. I mean, most specifically like data mining and mostly like orchestration. But then I went on and did biology. I mean, I worked in metagenomics because it was funny, and I mean, it was interesting, mostly. And then, yeah, I went back to IRCAM, and I've been an associate professor since. And this is where I created this little group. And now I supervise people that are great. Like, so.
It's fantastic. We have a question from Nick Bolka, who asks if you can give any examples of relevant papers that people could find for the library hypothesis.
The lottery ticket hypothesis, you can, I mean, I think if you type this in Google Scholar, you're going to get like maybe hundreds of papers, because the first paper is actually quite recent. It was maybe 3-4 years ago, I guess, like 2019 or such. And since then, there has been, like, first it was a lot of distrust. Like people would say, oh no, actually it performs as well as pruning and whatnot. but there has been like multiple studies that shows that no, it's not just, you know, random luck or anything. And so like right now, the problem of the lottery ticket hypothesis is if you want to make it work on a very complicated problem, so you have to train the model several times. And you have new types of approaches where you actually do it in a single pass. So my guess is it's, I mean, not the hypothesis in itself just shows that there is the possibility to find some super efficient solution to the same problem. So instead of wasting like billions of parameters, there is some solution. Problem is, how do we identify this? So we've been thinking, oh, more parameters allows us to not think about this question. But actually, there is like a huge possibility that we could identify ways of constructing the initialization or the way we actually look for the error landscape in order to find these solutions. So yes, specifically, I say you can start with the paper from Frankel and Carbin. So Frankel and Carbin are like the original authors from the first paper. And based on that, you just look at the, I don't know if that person knows Google Scholar. I think it's a great tool because you just type in and then you look at which papers cited this paper, and then you can just go recursively and you lose your whole life reading papers.
Fantastic. It looks like that's it for questions.
I had a question if there's time. Yeah, I wanted to throw out a question when you were discussing about kind of the deep double descent aspect as well, and kind of the over parameterization and the interpolation regime. Something that we've wondered about a lot is what that means in the context of, let's say, an audio synthesis problem, because a lot of that analysis is like for text or let's say image classification, where interpolation regime is probably much easier to achieve. I guess is kind of my point. Like if you just consider ImageNet dataset, the size of a model you need to interpolate the training set is relatively smaller, I think, than let's say you have a large data set of speech. Like to actually interpolate that, I think from a synthesis perspective is probably still beyond what anyone is doing in audio. So I'm just kind of curious if you have any thoughts on like what overparameterization or interpolation actually has in the context of audio synthesis.
Yeah, absolutely. That's a great question because we've been working on this exact problem lately. And the thing is, it's also depending on what's going on in the intermediate layers of your solution, right? Because the thing is that you have this grouping effect across the solution. So if you use dropout, for instance, the goal of dropout is actually, to break like correlations inside one layer. So you're going to have like clusters of subnetworks, and it's like a very recent paper showed that based on the structure of dropout plus, like for instance, ResNets, you can show that like lots of layers are completely useless in the computation. And so basically you have like a natural cluster is forming. If you have like, for instance, branches, you're going to have specialization. And a lot of things point out to there is natural organization dependent on the structure of the data and the structure of the network you're using. So I'm pretty sure the same goes actually for audio, because if you think about it, like we've all looked at these papers for hours where you have like the first kernels of the like every first layers, you're like, oh, it's Gabor filters. Wow, so amazing. And so basically, we know there is some inherent structure that is appearing. Then it's just a question of how you reorganize the structure. So for instance, we did like this quirky experiment with a PhD, and we just took the SVD of every layers, and we could see that this transformation, like the eigenvectors of every layer is almost the same if you just train like repeatedly on different data set or several models on the same data set, you almost get almost the same eigenvectors all the time, which kind of shows you that there is a possibility for finding commonalities. But I agree with you. The problem is mostly like in the end layers where you might have, I don't know if you know the network bending approach. So I love this, don't remember, I think it's Broad, right? Terence Broad, that wrote these papers about network bending. And we tried that as well. And that's super funny because, it's mostly not working with audio. I mean, we couldn't make it work. But it's also because it seems to work when you have like a huge network where most of the stuff is actually useless. So you just have these small effects. I'm pretty sure, yeah, there is some potential, yet it's going to require specific care for the generative aspect, at least.
Thanks.
Thank you.
Great. Any other questions? Just checking the chat. No, it doesn't appear to be any more questions from the chat. Thank you very much, Philip. Thank you for all your patience as well with the Wi-Fi.
Thank you. Yeah, sorry about the connection shit.
No problem. No problem at all. Great. So as we've said numerous times, if you're looking to get involved in the neural audio space, be sure to join our Discord. Link for that is in the video description. It's theaudioprogrammer.com/community. And with that, we could just move directly into our next talk. So for our next talk, we have Jatin Chowdhury, who is from Chowdhury DSP. Is it Chow DSP or Chowdhury DSP?
Oh, either one's fine.
Yeah, so
It's like an abbreviation.
Yeah. So if you're familiar with really amazing open source projects in the pro audio space, then you probably know about Jatin. He's created some fantastic ones like Chowkick and several others, and he's here to talk about a library that he has for creating neural networks. And I'm really curious to hear about this talk because I looked through the library myself and I had no idea what any of it actually meant. So today he's here to talk about his open source library called RTNeural. Over to you, Jatin.
Awesome. Thanks, Josh. Yeah, and thanks everyone for having me. I'm really excited to be here and to be talking about this. And yeah, I wanted to say thanks to Philippe as well, because I really appreciated his talk. I feel like he kind of comes from a similar perspective as where I'm coming from, as you'll see in a moment, but then kind of approach it in a very different way. So that was very informative for me also. But yeah, I'll go ahead and share my screen here. Hopefully you all can see this. Yeah, so I've got I've got some slides here. I think I shared the link with Josh. If you're able to share that with the folks who are watching the stream, that would be fantastic as well.
Yeah, I'll do that right now.
Awesome, thanks, Josh. Yeah, so I'll just be talking about creating neural audio plugins with RTNeural and explaining a little bit more about what RTNeural is along the way. So some of you probably know me, but I'm sure a lot of you also don't. So I'm Jatin. I currently live in Seattle, and before I was here, I worked at Tesla for a little bit, and then I was at Karma for a little bit. And most of the time that I am around, I spend making audio plugins, and a lot of them are open source. So if you're curious about checking them out, I've got some links here as well. So kind of the original idea behind RTNeural started back in 2020 when I was taking a class at Stanford, and this was right around when COVID was getting started, so everything was in a bit of a weird time. But towards the end of the class, we had to do a final project, and so for my project, I decided that I was going to do basically a neural audio plugin that was meant to emulate the Klon Centaur guitar pedal. And one thing that made this project hard was that I only had about 2 weeks to do the whole thing. So that was kind of a tough limitation for me at the time. But I was able to kind of get started and train a neural network that sounded, it wasn't perfect, but it was reasonably close. And then I ran into some problems when I tried to actually deploy my network in my plugin. So at the time, I was using a recurrent neural network. And I wanted to use TensorFlow Lite, but the TensorFlow Lite system did not support recurrent neural networks at the time. I think they do now, but this was a couple of years ago. I also looked at using PyTorch's C++ system, but their build system was a bit complicated. I had some trouble getting it to work, and that caused even more problems when I started to look at deploying the network on an embedded device. So I wanted to run this on an Arduino. I think it was a Teensy or something like that. And there was no way I was going to be able to get the PyTorch system to work for the Arduino build system. So what I ended up doing was just writing my own little inferencing code in C++. And I don't know, that seemed like kind of a daunting task at the time, but I had a previous homework assignment that I'd done for the class that kind of laid a lot of the groundwork for this. So I was able to actually get it done in sort of a rough and not very great implementation, but good enough to get me through the class. And so that was sort of where I started working on the code that would become RTNeural. And eventually, maybe some months later, I came back to it and I was like, maybe this would be useful to have as kind of a separate library. So rather than being some code specifically for this plugin, maybe I could take this neural inferencing engine and make it its own thing, and then use that in whatever other applications I want to use it for. And so when I started thinking about this, I kind of had to grapple with this question of like, well, what does the world need with another, library that can do neural network things? Because at the time, these libraries like PyTorch and TensorFlow had been around for quite a while. And obviously these libraries have some pretty hefty engineering effort behind them. There's engineers at Facebook and Google and Microsoft and all these big companies who are just working on it regularly and trying to make it really good. And so I figured that whatever neural network library that I made shouldn't really try to replace these things just because I wouldn't have the resources to do that, or not that I even really want to, because they're good at what they do. You can do a lot of things with them. You can train your networks, you can do inferencing, you can do analysis and hyperparameter tuning, you can support all these different hardware platforms, you can use them for audio, for language processing, for whatever you want. And I figured that if this is just going to be a library that I'm probably just going to be working on by myself for the most part, or at least to get started, I should try to start with a much smaller sort of target. And so the idea for RTNeural is that it was meant to be used for much smaller and more specific use cases. So first, I decided that RTNeural would not have any training in it. So you can't train a neural network in RTNeural. You can only run inferencing. I also decided that I would only try to run on CPUs. Maybe we'll change that in the future, but for now, that's kind of where it's at. And I also decided that we would try to maintain a pretty strict adherence to the rules of real-time audio programming. I'll talk more about this in a second. It's also focused mostly on audio processing, just because that's what I know best, but I imagine some of the ideas might be useful in other fields too. And we're also focusing on smaller network architectures, and I'll talk more about that later on as well. So that leads to what RTNeural is today. And so basically, it's a neural network inferencing engine that's written entirely in C++, and it's focused on real-time applications. So sort of the general workflow, which I'll go through more in a little bit, is that you train a neural network, probably in Python, but you could use whatever system you like for training it. Then you export the weights from the neural network into some format. Then you write a C++ program, and in that C++ program, you can use RTNeural to run inferencing on your neural network. And we'll go through this in a bit more detail pretty soon. So I also wanted to talk a little bit about real-time safe programming. This isn't going to be a comprehensive discussion of this. It's kind of a big topic. But sort of the general rules that you have to follow are, first of all, you don't want to allocate memory in your real-time process. So maybe you have some memory that's allocated ahead of time. That's fine. Maybe you have some memory that's allocated on a separate thread and you have some lock-free way of getting it into your real-time process. That's fine too. But in your real-time process, you don't want to be allocating memory. You also don't want to wait for other threads. So if you have to lock or unlock a mutex or something like that, where you're interacting with another thread and kind of waiting for it to do what it needs to do before you can continue doing what you need to do, that's not something you want to be doing in the real-time process. We also don't want to wait for external hardware. I'm not going to talk too much about that one. But yeah, if you want some more information about real-time audio programming, this is a great article that I read kind of when I was getting started with audio programming. And I don't know if it's a little bit dated now, but it's most likely still very, very useful and very helpful. So definitely check it out. So kind of the question then is, do these larger neural network libraries follow these rules? So if I were to try to use PyTorch or TensorFlow for running inference on my neural networks, would it be real-time safe? And the answer is that it's kind of hard to know. So if you dig through the code in these larger libraries, there's often so many layers of abstraction and so many things that you have to dig through that it's kind of hard to figure out what they're really doing internally. I believe when I was looking at some PyTorch code a little while ago, I don't think it was real-time safe, but again, maybe there's some tricks that I wasn't able to see through the abstraction that make it more real-time safe. I had heard from someone who had worked on it that TensorFlow Lite and TensorFlow Lite Micro are meant to be real-time safe, but I haven't tried to confirm that myself. And then, yeah, I spent some time looking at Onyx a couple weeks ago after Oli Larkin's talk, and I think it's real-time safe, but again, it's a little bit hard to tell through some of the abstractions. There's also something that we like to think about in audio programming about sort of the performance concerns in our program. And kind of what's interesting to me is that the types of things we think about for performance in audio programming are often a little bit different than what you might think about in more general computing problems. So in audio, we think a lot about math optimizations. We think about how do we reduce the number of multiplies we're doing. Maybe we want to use some explicit vectorization with SIMD intrinsics. Maybe we want to use some approximations for some math operation that might take a little bit of a long time. We also think about memory effects sometimes. So we want to try to minimize cache misses. We want to try to use stack memory and contiguous memory whenever we can. And then we also think a lot about function call optimizations, or at least I do. So when you're calling a function once per sample, you want the overhead of that function call to be as small as possible. And so particularly if you're calling this function through some kind of virtual or abstract interface that the compiler isn't able to optimize through that interface, then that's going to kind of slow your program down. And I put a little link here for a website that talks a little bit more about some of these different ways you could call a function and some of the overhead associated with that kind of thing. And what's interesting, again, to me is that if you were to talk to someone who does more general computing, you might see more things about, for example, parallelizing your operation over multiple CPU cores and things like that. Or maybe using specialized hardware like a GPU or something. And these are things that we do experiment with in the audio world, but they add a lot of complexity to your problem. So I find that most people want to try to get as much as they can out of their one CPU core and try to drive that to the maximum possible usage before they expand to these more complicated solutions. So the sort of idea for RTNeural, kind of the goals for the project, are to provide the best possible performance for running inference on a neural network, especially a smaller neural network. We're also trying to be as flexible as possible. So we want to support some different neural network layers. We want the library to be extensible. So if you have a custom layer that the library doesn't support, you should be able to implement it yourself without too much difficulty. And then we also have different computational backends, which I'll talk about a little bit more later on. But we're also trying to make the library be very lightweight. So libraries like PyTorch and TensorFlow, they really want to support everything. So everything you could possibly imagine doing with a neural network, these libraries want to support. In RTNeural, we have some smaller goals. So we want to support the basic things and make it possible for you to implement your own things if you want some more custom behavior. But we're not going to try to support everything because that would just make the library way too big, and we want it to be pretty small. We also want it to be easy to compile and fast to compile. And for right now, one of the ways that we do that is by providing simple integration with CMake. I know folks who aren't using CMake have also used the library successfully, so it's not too difficult in other environments as well. So these are some of the things that RTNeural supports currently. So right now it's C++ 14 or later. We're not trying to go back to C++ 11, but I'm glad that we were able to at least get C++ 14 in there. We have support for some pretty common layers like fully connected and an LSTM layer, and for a lot of pretty common activation functions. I also wanted to shout out Stepan and Damien and Wayne for contributing the layers that you see there. Yeah, there's some great work that folks have contributed. So yeah, I've been very happy to not have to do all of the work myself. There's been some fantastic contributors who have made some great changes to the library. So thanks, guys. And then, yeah, so if you're using plugins regularly, you might have used RTNeural before, whether you know it or not. So RTNeural is open source and is licensed under a BSD 3-clause license. So that means people can use it for commercial products and things like that if they want. And currently RTNeural is being used in a number of open source plugins and commercial plugins. So some of my open source plugins and some open source plugins made by the GuitarML project use RTNeural. There's also a number of commercial plugins that either I've worked on or some friends of mine have worked on that use RTNeural as well. I'm not sure which ones I'm allowed to talk about, so I don't want to name any names just in case. But they're definitely out there. And again, because of the way that the library is licensed, there could be other commercial plugins that I don't know about. But yeah, if you're using RTNeural, definitely email me and I'll add you to our, we have a little thing on the GitHub page for projects that are using RTNeural. So I'd be happy to add more people to that list if people have projects. So cool. So I'm going to get some water, but I wanted to talk about developing a plugin using RTNeural. So let's say that you're working on some neural network model and it sounds amazing and you're like, oh, this is the best thing ever. It's going to be an amazing plugin. And so now you're ready to deploy your model in a plugin. So the way that you do that with RTNeural would be something like this. So maybe if you're working in TensorFlow, you create your model as sort of a sequential model. If you're doing a non-sequential model, then things get a little more complicated. But for now, we'll say it's sequential. So you create your model and you add your layers to it and you train it and everything's great. And then all you have to do is import this function from RTNeural. So RTNeural provides this function for you called save model, and it will save your neural network model to this JSON file that RTNeural will know how to deal with. If you're working with PyTorch, things are a little more complicated. We're still working on improving our PyTorch support in RTNeural. But basically, again, you would create a model and you would train it. And then you can use this method basically to export the neural network weights, again, to a JSON file, but this will be kind of a different JSON file. So we'll need to do a little bit more work to actually load it into the network on the C++ side. And this is all stuff that you can find in PyTorch, and this is just the regular Python JSON module. So there's nothing RTNeural specific in this PyTorch example here. So now you're in C++ and you say, okay, well, I need to load this JSON file so that I can load it into my network. And so in RTNeural, we use this nloman JSON library that's reasonably popular. And so, for example, maybe you're trying to load your model from a file that's somewhere on your disk. Maybe you could use the standard file system library. And so basically, you'll create an input stream, you'll load that into the JSON object, and then you'll return it. And that's kind of all you need to do. Or maybe you're working in like a juice kind of situation and your model is in binary data. So if you're working in that kind of situation, you can just create a memory input stream from the binary data, read that into a string, and then use that as a JSON object there as well. So now we're going to construct a model. And first, we're going to show how to do this through the dynamic API in RTNeural. And so the idea with the dynamic API is that you just create some kind of abstract model type, which we'll call RTNeural model. And then you'll parse the JSON file, and that will give you the network that you want. So if you're working from TensorFlow, this is really easy. It's basically just 2 lines of code. You create your model, and then you parse the JSON file, and you have a model. In PyTorch, you have to do a couple extra steps. So basically, you can create your model. Again, it's just this abstract model type. You get your model JSON object, and then you have to create each layer yourself. So maybe your first layer is a dense layer, so you can create that. You give it some number of inputs and some number of outputs, and then you can load the weights and the bias for that layer on your own. So you just get these from the JSON file as vectors or 1 or 2D vectors. And then finally, you just add the layer to the model as you see below here. Or maybe you want to work with the RTNeural static API. So in this case, you actually define the model type at compile time. So that's what we're doing here. We're saying, okay, our model has some number of inputs and some number of outputs. It has a dense layer with some number of inputs and some number of outputs. And then maybe it has some other layers here as well. But yeah, we'll ignore that for now. So you create your model. And then again, if you're working from TensorFlow, it's just one line of code to load the model weights from your JSON file. You can just call parse JSON and you're good to go. In PyTorch, it's kind of the same thing as we saw on the last slide. So you get your dense layer and then you load the weights manually, again, by just grabbing the correct thing that you need from the JSON file. And so then let's say you're ready to process your audio now. So maybe you have some kind of process audio function that uses an audio buffer. And let's say that this neural network has one input and one output. So you would want one model per channel that you're going to process. And then in your processing function here, you would loop through your channels, you would loop through your samples, and then for each sample, you could just process it through the correct model. Like this, and it should be pretty easy to work with. If you have more than one input and more than one output, you have to do a couple of extra steps, but it's really not too bad. So yeah, that's where we're at. So along the way, you've kind of got to make a few choices here. So one choice that you might make is TensorFlow versus PyTorch, and there's lots of different reasons why you might want to choose one or the other from kind of a training perspective. But yeah, from RTNeural's perspective, if you're working in TensorFlow, then it's a little bit easier to do some things. So it's very easy to save your model. RTNeural gives you a method to do that. It's very easy to load your model using the JSON parsing logic in RTNeural. Then if you want to run the model, it's pretty easy, like I just showed in the last slide. If you're working in PyTorch, then you have to do a couple of different steps and a couple of extra steps. So when you save your model, you have to use this state dict object in PyTorch and dump that to your JSON file. Then when you load the model, you have to do a couple of extra steps where you configure your weights as a vector or a multidimensional vector. And then when you load the weights for each layer, there's a couple little gotchas where maybe you have to restructure the weights in some way, like for example, if you have I think it's a gated recurrent unit, then one of the weights or a couple of the weights matrices have to be transposed before you can load them into RTNeural. But yeah, that's some stuff that we're still working on, trying to make it easier to load PyTorch models. So hopefully that will get even easier as time goes along here. And then when you go to run the model, it's exactly the same between PyTorch or TensorFlow. So next, let's talk about the static API and the dynamic API. So the idea with the dynamic API is that the model architecture can be known at runtime, but it doesn't need to be known at compile time. And so because of that, any internal memory that the model needs will be heap allocated rather than stack allocated or locally allocated. And so what you end up with is a very flexible model that could load anything pretty much, or anything that RTNeural supports. The static API is a little bit more restrictive because you have to know the model architecture at compile time. But if you do know the architecture at compile time, then that's much better in general because the compiler can see through everything that the model needs to do when it goes to process some audio. So it can do some optimizations like inlining function calls, unrolling loops, improving cache locality, all kinds of stuff like that. So whenever you're able to, definitely use the static API. It's much faster. But if you need the flexibility of the dynamic API, then that's good there too. And then finally, RTNeural has this idea of a backend, which is basically sort of the engine that RTNeural will use for actually doing the internal computations that it needs to do. So the most simple backend is the standard library backend, and it's great because it has no dependencies. So you don't need any libraries or any additional code aside from just the regular standard library that your distribution of C++ should provide for you. The negatives are that we can't do any explicit vectorization using the standard library, and so it has the worst performance of the three backends, but it's also the most portable. So if you're running on an embedded device, or if you're running in some context where these other backends may not compile, the STL backend will pretty much always compile, and you can use it for whatever you need. The eigen and xsimd backends are there for better performance. And so with eigen, we're using the eigen library, which is a pretty common sort of linear algebra library in C++. Eigen has some devectorization that it does internally. And another advantage of eigen is that all the code ends up being very readable, because all of the operations are kind of spelled out in these eigen operations, which are pretty easy to see what they're doing just from reading the names. With xsimd, we're using the xsimd library, which is basically like a C++ wrapper around some SIMD intrinsics. And so there we're using our own custom implemented matrix operations that explicitly vectorize certain operations using these SIMD intrinsics. There's some spots where I think it's a little bit less memory efficient than eigen, just because we're padding some vectors and things like that. But the performance between eigen and xsimd in terms of CPU usage is pretty comparable. So typically what I'll do is just compare the performance between the eigen and xsimd backends for the specific network architecture that I'm working with and for the specific target platform that I'm trying to work on. And then when you go to pick a backend, you can do this pretty easily if you're working in CMake. Basically, you just define one of these three definitions here. So you pick xsimd, STL, or eigen, and then the CMake configuration will do the rest for you. So yeah, I've been pretty happy with talking to people who've been using RTNeural. In particular, I was talking with Keith, who works on the GuitarML plugins, and we started talking around when he was working on the NeuralPi project, which is basically a Raspberry Pi powered guitar pedal that runs some neural network models on the Pi. And when we started talking, he was using a LSTM model that he had written the code for. He had borrowed from someone else. I don't remember exactly where it came from, but we ended up porting his model over to run in RTNeural, and it ended up being a pretty significant performance boost for that implementation. So I was very happy to see how well that worked for him. And yeah, overall, I've been pretty happy with the performance benefits that we've been able to get from the static API. In general, I found that it's about 2 to 4 times faster than the dynamic API. So I'm really happy with how those optimizations have worked out. There we go. Yeah, so we've also done some performance benchmarks. So this is comparing RTNeural against the PyTorch C++ implementation. And so what you're seeing here is basically how many times faster than real time a certain layer is at a certain size. So for example, here we have a dense layer with 4, 8, 16, and so on inputs and outputs. The dashed red line here is kind of our real-time limit. So anything below the dashed red line can no longer run in real time, at least at the sample rate where we did these benchmarks, which is 48 kilohertz. And so as with RTNeural, as the layer size goes up, generally the speed goes down a little bit. PyTorch seems to be a bit more stable, and I think part of that is because they've optimized themselves a little bit more for handling really, really large networks, which makes sense since they need to be able to, people need to be able to use PyTorch for like massive image processing networks and video processing and things like that. Whereas with RTNeural, we've tried to optimize a little bit more explicitly for these smaller layer sizes, since oftentimes that's what you might find in an audio processing or an audio processing network that's meant to be used in real time. Yeah, and so we've also got a bunch of resources here. So all of the code for RTNeural is up on GitHub, and there's a link there. I wrote a little blog about it a couple of years ago. Maybe it's a little bit old now, but some of the information there should still be pretty useful. There's also a little paper that I wrote on the archive that just kind of describes a lot of the things I've been talking about here, maybe in a little bit more of a technical way. I made a little example plugin that just kind of shows how to use the static API and the dynamic API. So if you're looking at implementing a plugin, that's probably a good resource for you as well. And then more recently, I put together an example plugin using the standard variant type. And the idea there is that we were experimenting with trying to make the static API be a little bit more flexible and behave a little bit more like the dynamic API. So that was a pretty fun one to work on. And then there's also the repository for the benchmarks. So that's the repository for generating the plots that were on the last slide. And I'm hoping to improve that at some point so that, you know, we can compare against TensorFlow and maybe Onyx and some other inferencing engines. I think that would be useful. But yeah, so in general, RTNeural is still a work in progress. So we're trying to improve our support for PyTorch models and add support for more layer types. I was also thinking it would be cool to have some kind of model library where there's kind of a place where you can just get some commonly used network architectures that are already implemented in RTNeural, and you can just kind of pull them into your own project if you want. As I mentioned, kind of the first priority with RTNeural is performance. So we're always trying to make the performance a little bit better. And if you have some ideas for how to do that, we're very much open to suggestions. And then, yeah, so recently we've also been looking at improving our, or adding some methods for approximating some more computationally intensive functions like TANH activations and things like that. And then probably the thing that's hardest to keep up with the major neural network libraries is documentation. So that's something that we're always trying to improve and do a little bit better on. So yeah, if you have time or energy or feel like contributing to any of these things, that's always appreciated. And yeah, thanks everyone for listening. If you have questions, I'm on email, I'm on GitHub, and I'm on the Audio Programmer Discord as well. And so yeah, thanks to everyone for listening. Thanks to Josh and the folks running the competition for having me on. And yeah, thanks to everyone who's contributed to RTNeural. I know I mentioned some of you guys a few slides back, and then also Matthias, who I think is also on the Audio Programmer Discord, actually made this logo for us. So thanks to him for that as well. It looks pretty cool.
Yeah, pretty sweet logo. I love that. Cool. Thank you so much, Jatin. Just going to give a couple seconds, minutes for people to ask any questions that they may have in the chat. Any questions from our guests, from the hosts? Anybody? Cool.
I had one question just for Jatin on you know, like a lot of the RTNeural stuff and examples that you've shown so far have been kind of mainly in the sort of area of like you know, either like AMP emulation or analog hardware emulation and things like that. Have you ever like thought about trying to apply the RTNeural stuff to I don't know, maybe like a neural audio synthesis effect or you know, timbre transfer or something like that to see how it performs or may help, you know, improve the performance of some of these architectures?
Yeah, definitely. I don't know that I've necessarily tried to like explicitly like take an existing architecture and convert it into RTNeural, like for example, like the DDSP network or like the RAVE network or things like that, or those architectures. But yeah, I have experimented with doing other things. Like I've messed around a little bit with just trying to get a network to generate a waveform based on some random input, and then you could use that in like a synthesis kind of scenario. Yeah, I've been I spent a little bit of time playing around with like trying to process some biomedical data just to see if I could do something fun with it, but I never really came to anything. So yeah, I'm always trying to experiment and do different things with it. I think I end up in sort of the analog modeling world a little bit, just because that's something I'm familiar with from kind of doing circuit modeling research as well. But yeah, I try to do different things, and kind of one thing I'm hoping with the neural audio plugin competition is that people will do some fun things with it, and then I'll get to see that and get inspired. In other
Definitely,
ways
hopefully. No,
yeah.
that's my curiosity as well. Like it'd be really cool to see it being applied to like in other ways and see it, like for example, how much performance we can squeeze out of maybe some of like the timbre transfer models that are going around as well. Like if, you know, in comparison to running them in like PyTorch or you know, TensorFlow and stuff like that, like how much more performant they are, maybe using RTNeural, for example. Be interesting experiment.
Yeah, definitely.
So we have a question from Nick Bolka who asks, could this work real time in the frequency domain after an FFT?
Yeah, so this is actually something that Damien, who I mentioned in the talk briefly, he was in touch with me recently, and we were talking about this. And so I think he's doing something kind of along those lines in the competition here. So he had contributed a two-dimensional convolution layer to the library. And so yeah, really, like, you can put anything you want as the input or output to a network in RTNeural. In my use cases, it's typically like a time domain signal. So maybe it's one sample, or maybe it's a couple of samples if you're doing like stereo or multi-channel audio. But yeah, you could, let's say you have an FFT that has, I don't know, 512 numbers coming out of it, and that would be your input to your network in RTNeural, and then you could do whatever other operations you need to do from there. Oh, I think you're
muted, Josh.
I always do that. I'm a ventriloquist. Jatin, thank you very much. Looks like that's all the questions that we have in the chat. Thanks again for your talk. Really exciting project.
Awesome. Thanks, guys.
Yes.
I do have a question, if that's okay.
Of course.
Sure.
Yeah, I'm wondering if you're looking into like spiking neural networks and this type of, because there is, I mean, we're talking about real-time computation. If you think about like languages like SCADE, I don't know if you know.
Not familiar.
SCADE or Estral, because like I love the fact that you put some safe real-time specifications, because there is also like critical, if you think about, I don't know, like nuclear plants, all this type of stuff, you need like hardcore. I know like guitar effects is not the same level as, nuclear plants, but it's kind of the same kind of hard constraints that you need on your language to work. And that's why, some logic languages have been developed like SCADE. And it's basically like lots of, useless math. But in the end, like the principle of a network itself is not a real-time function, right? So getting closer to something which is akin to signal, because this is what we're trying to emulate there. So I don't know if you have a take on where should we go to have, like, if we could change the way the architectures work. That's why I was thinking about spiking neural networks, for instance, to be a lot closer to what's actually going on when we're looking at, acoustic and electrical signals.
Yeah, that's a good question. Yeah, I think that's interesting, because I think kind of the approach I've been taking so far with RTNeural has kind of been the other direction, where I'm like, oh, this is what the machine learning people want to do, so I'll try to get my stuff as close as they can in that direction. But yeah, going kind of the other way, I think maybe the easiest thing, or the thing that would make the most sense from sort of a signal processing perspective, would be to have maybe like some form of a neural network that is like collapsible, where you can kind of collapse the whole thing into like one or two matrix multiplies, or one or two simpler math operations, or something like that. I don't really know if or how that would work on the training side of things, but I think that would be kind of cool. Another thing that I've been thinking about is like taking things that we're used to doing in signal processing, like, for example, some of these numerical approximations, or things like lookup tables and stuff like that, and just kind of using those on the training side, so that or something that I've noticed in the past is that, like, if I train my network with a tanh activation, and then I change my activation function on the deployment side to like some approximation, it doesn't always sound the same, because the network was trained with the properties of the original tanh function. And so I think that training with approximation functions and things like that could be a useful thing to do as well.
Cool, thank you.
Yeah.
And is there any other backends, Jatin, that you're like
Looks looks like our internet speed is
as well,
problems.
or anything that's kind of on your radar. Was that me? Can you hear me now?
Yeah.
Yep, you can see there now.
Looks like
Yeah,
whatever
sorry.
Philip had, you currently have now.
Oh no. Okay, that's not good. Yeah, hopefully you can hear me now. I was just asking Jatin if there's any other like backends that you're like considering for the future, or thinking about
Yeah, so I
extending
had spent
for
some
other like
time.
backends and stuff.
Yeah, so I'd spent some time a little while ago using sort of the Accelerate library on the Apple devices as kind of a backend, and it was okay. It was pretty decent, but I kind of stopped supporting it just because it was a lot of effort to maintain for something that I could only use on one platform. But something I've been thinking about more recently is maybe, especially with some of the M1 Macs that are out there now, is they have their like little neural chip in them. So if there was some way to utilize that, that's something I've been looking into a little bit or thinking about. And yeah, I've looked at some other different math libraries like Armadillo, and there's another one called, I think it's called Fastor or something, that was supposed to be pretty fast as well. So yeah, I've been looking into some different things, but yeah, adding a new backend at this point is a little bit more of a kind of daunting task now that the library has grown a little bit. So I think I would need a pretty good reason I would need a pretty clear advantage over one of the existing backends to kind of want to try something like that. But yeah, like I mentioned, performance is the most important thing. So if there's something that seems like it could be the fastest, then I'm definitely willing to go that route.
Awesome.
Okay, looks like everybody's had their questions answered. So yes, thank you again, Jatin. Thank you very much, Philip. This is really fantastic talks. Thank you very much for this. Like I've said before, to find out more information about the competition, be sure to check us out on theaudioprogrammer.com/neural-audio for information about the competition, and join our Discord at theaudioprogrammer.com/community. Links are in the video description below. And some people have been asking if this video will be available to watch afterwards, and it will. So you can watch it right after this is over. So we hope you enjoy it and find it useful. We're looking forward to hearing some more productive discussions about collaborations and seeing what people come up with. Any thoughts? Andrew, Christian, anybody? All right, don't chime in all at once now. Yeah, speechless.
Yeah, no, nothing more to say. I just thoroughly enjoyed these talks tonight. So just looking forward to seeing how it inspires the participants and potential participants, and I look forward to seeing like more discussion relating to RTNeural and the work and research at IRCAM, like been discussed in the Discord, and yeah, looking forward to the next set of streams.
Fantastic. So next week, if my memory serves me correctly, we actually have a PhD student special that Christian has been working on especially. And would you like to tell them a little bit more about what's coming up next week?
Yeah, sure. So I'm really excited about our session next Friday at the same time. And we're going to have 4, potentially 5 PhD students from all different universities that are working in the kind of intersection of neural audio, audio effects, and music production to kind of give us very quick lightning talks in some sense about the takeaway messages from their kind of latest research in this area. And so I think we kind of reached out to a lot of people and tried to get some PhD students that we thought were working on topics that would be super relevant to the audience here, which is, I think diverse, but people that are working in machine learning, but also people that are audio developers or DSP nerds as well. So I think I'm really excited to kind of see the mixing of ideas that we'll have next week. And I think we'll be announcing the names of who will be presenting early next week. So I'm really excited for that. Definitely attend.
Awesome. Great. So as you were talking, there were two questions. One that I was going to get to anyways, and another one that's more technical. We'll go with the more technical one first for Jatin. How much data are people using to train RTNeural for a reasonable result?
Yeah, so it kind of depends on the network that you're trying to train. And I think it's a little bit more general than just like specifically for RTNeural. So typically you would train your network using TensorFlow or PyTorch, and whatever kind of architecture you're working with, you can kind of evaluate within that context. So like in TensorFlow, you could train your network and then test it on some validation data set or something like that and see how good your accuracy is, and kind of decide how much more data you might need from there. And then, yeah, RTNeural is kind of assuming that you've already trained it on enough data once you bring your network into RTNeural. But it kind of just depends on the specific use case from there.
Great. And the other question was one that Christian and Andrew and I actually discussed right before we went on the live stream, which was that some people have been asking about the possibility of a week extension for the competition. It's something that we'd very much like to do. We're just checking and making sure that our judges would actually be able to join us for the final live stream 1 week later than originally scheduled. So once we hear back from them and get approval from them, we hope that we could do a week extension, but can't promise it just yet until we hear back from them. So yeah, great. And with that, if there's nothing else, I'll go ahead and sign us off. Thank you very much. Thanks to Jatin and Philippe for the talks. Thank you, Andrew and Christian, as well, for being awesome co-hosts and for making this possible. And thank you to our sponsors as well for being supportive of this initiative and supportive of the competition. And with that, we'll go ahead and sign off. Everybody have a great day, morning, evening, or afternoon, wherever you may be in the world. And we will see you next week. Same time, same channel.